this is the case. Huh? Yeah, so what it's saying is you're going to take the antiderivative of the inside, and then instead of having to do Riemann sum, or the geometric interpretation by using geometric formulas to find the area, you're going to use the antiderivative. You're going to plug in the upper limit, you're going to plug in the lower limit, and then you're going to subtract upper minus lower, always. It's not small minus big or big minus, it's always whatever number's at the top minus whatever number's at the bottom of your limits of integration. Why is this so important? No more Riemann sum. On the test, you will probably see Riemann sum of some sort, some fashion. But at least from then on out, you won't need to do Riemann sum because of this awesome theorem. So here's the notation that we're going to use. We're going to, instead of writing f of b minus f of a, we're going to find f of x. And we're going to use this notation here. So I'm just going to show you how it works. But it's really useful for keeping track of your work. That way you don't have to do everything in one step. Find the antiderivative and plug stuff in. Find the antiderivative with the bracket saying I need to plug in a and b, and then you plug in a and b. So first of all, you have to find the antiderivative. So what's the antiderivative of this integral? Well, x to the third, what would that be? Parallel antiderivative, so you add 1 and then multiply by the reciprocal, minus 2x, add 1 to the power, so it's squared, and divide by the new power, plus 3 is a constant, so we just go on the next. You can put the plus c. However, both of these are going to have plus c. So what happens when you subtract the two c values? They cancel out. Okay. Whatever c you use for one, it would be the same c for the other because f is f. So whatever one you pick. You pick any one you want. What we're going to do is pick the one where there's no c. C is 0. So this is our capital F of x here. And then the notation said at the end we put these brackets. We put our limits of integration. So our limits of integration were -2 to 3. We're going to put -2 to 3. You want to put a bracket in the front to make sure you understand all of it has to be evaluated between those two values. That's fine as well. It's better, but I'm a little flexible on that. Alright, so the rule says you plug in b first, the top number first. So this guy is going to go in first, minus this guy. Alright, so we plug 3 in. So 3 to the 4th power would be 81. So 81 over 4 minus 2's cancel out. So 3 squared would be 9. Plus 3 times 3 is 9. Perfect. So this is what we get when we plug in 3. That is f of b. Minus, we need to plug in f of a. To find f of a. All of this is going to be f of a. So if we plug in -2, to the 4th power, that's going to be a positive. 2 times 2 is 4, and then 16. So 16 divided by 4 is 4. Minus a -2 squared is going to be a positive 4, but it had a negative out front, so it's still negative. Minus 3 times -2 would be -6. There's your f of a. It wasn't so bad, I hope. If you have questions, let me know. I'm going to do a couple more examples. Simplify. Whatever you can. So -9 and +9 cancel. -4 and +4 cancel. Okay. We have 81 over 4 minus a -6 or a +6. Now we're going to get a common denominator here. So 6 is over 1. So multiply top and bottom by the 4 that you need. So 81 plus 24 all over 4 plus 105 over 4. And there you go. So what have we just found? This is the integral of -2 to 3 of our function. If f is positive over the limits of integration, this is the area under the curve. If not, it has other types of interpretations. Those applications we really don't talk about a lot. You'll see a little bit when we talk about area again in a few minutes. Alright, let's find the antiderivative, and then we're going to evaluate the function at the limits of integration. So, antiderivative of 1 is x. What's the antiderivative of cosine of x? Sine of x. Put your brackets on, write your limits of integration. keep them in the right order. We plug in the top limit first. So if we plug in pi, we get pi plus sine of pi. Minus, we plug in 0, we get 0 plus sine of 0. 0 is your friend when it comes to limits of integration. Usually, when you plug in 0, everything is gone. However, trig functions are an exception to the rule as well as ln, because that's a problem area. We'll talk about that in class 2. Alright, so we have pi plus what's sine of pi? 0. Minus 0, that's gone. What's sine of 0? 0. So the whole thing becomes pi. Like I said, if this function is positive from 0 to pi, then this would be the area under the curve. Okay. Let's try another one. Integrate. Value. Oh boy. That's not a very nice format for running antiderivatives. So what do we need to do? Well, let's bring the bottom up. Let's get rid of the fraction by making it a negative x. There was some integration on there. Alright, that's better. That's a power rule with a function inside. Oh, this one is a simple one, because what's the derivative of the inside? The derivative of the inside is just a 1. But I actually have an extra 3. So let's take that 3 and put him outside. Alright, so now we have the 3 outside. Integrate from -2 to 2 of x plus 3 to the -4 dx. So, derivative is just 1. Well, that's it right here. So that's taken care of. So all of this is the 1 and the dx are taken care of. When you do the antiderivative, we just have to do the power rule and keep that 3 in front. So x plus 3, add 1 to the power, and then multiply by the reciprocal power. So we get the negative on the reciprocal. Hoping this all makes sense to you all. I don't have you here, so I can ask you. Email me if you have questions. 3's cancel. Oh, what did I forget? I don't need plus c, but I do need my bracket to remind myself that I have to evaluate this over my limits of integration. Alright, before I evaluate this, I'm actually going to rewrite it as a fraction to get rid of the negative exponent. It'll make evaluating it easier. So -1 over x plus 3 to the 3rd power, -2 to +2. Alright, so plug in the 2. -1 over 2 plus 3 is 5 to the 3rd power. Minus, we plug in the -2. So a -1 over -2 plus 2. That is 1 to the 3rd power. So we have -1 over 5 cubed is 125. These two negatives become a positive. 1 over 1. Okay, I really need a denominator. 125. So 1 over 1 is 1. The common denominator, that's 125 over 125. Combine together, and you want 124 over 125. No. Yeah. I have one more here. Yep. Alright. Pause the video. You try it. If you haven't been trying it already. Pause the video. You try it. Find the antiderivative, and then plug in your limits of integration. Come back and see what happens. Alright. So the antiderivative. 3x to the 2nd power, which is power rule, divided by 2. Oh, wait a second. Before we do that, we should find out algebra first. Let's fix the square root. How should we write the square root so that we can take the antiderivative? The root is 1/2 power. Alright, now we're ready. So, 3, we add 1 to the power, divide by the new power. Plus, x, add 1, so 1/2 plus 1 is 3/2. And we multiply by the reciprocal of the new power. Don't put plus c because you need your bracket and your limits of integration. We plug in 9, so we 9 squared is 81 times 3, so 243 over 2. Plus 9 raised to 3/2. Alright, let's talk about that real quick. X to the 3/2 is really the square root of x to the 3rd, or square root of x to the 3rd. Usually we want to take the root first before we do the power. We'll make the number smaller before we go bigger. So in our case, this is the square root of 9, which we can find, raised to the 3rd power. Or 3 to the 3rd, which is 27. plug in 9, we get 2/3 times 27. This is our f of b. Minus, if we plug in 0, what happens? Everything's going to be 0. So that's just wrong. That's what I meant by 0 is your friend. Remember the integration. So what do we have? 243 over 2. Can't reduce that. The 3 and the 27 can reduce to 1 and 9. And then plus 2 times 9 is 18 over 1. Common denominator is 2. So we have 243 plus 36 all over 2. Or 279 over